Okay. So, in our last class. Yes?
Your recording is on. Okay.
Yeah, I have already recorded. Yes, sorry. Okay. So, in my last class, what I did, if you recall, I did arc length, and before that, I did length of a curve in space. Okay, so we have already derived formula for all those. Okay, so what we are going to do now, we are going to move to the concept of curvature. Concept of curvature. Okay, so what is curvature? Now, let me consider a curve. Let me consider a curve in 3D space. 3D space. Suppose like suppose it is like this. Suppose it is like this. Okay. So now if the curve is such that at each point lying on the curve, we can draw a tangent. We can draw a tangent. Then this curve is called smooth. Probably you already know it. This curve is called smooth. Okay. So the prerequisite for smoothness of the curve is that this r prime t, it exists, and of course that is not the only thing. And r prime t, it should not be equal to 0. Okay. So now, since the curve, it has been parameterized to the parameter t. Also, if this condition is satisfied, then we say that the parameterization is smooth. So you may be thinking, why I have been broaching up all this, smoothness concept here. Okay. So now, again, in order to be smooth, what you should not have, something like abrupt or sharp corners, or your cusp. You shouldn't have them if the curve has to be smooth. This we don't want. Okay, so I shouldn't get something like this. So that means here I have a sharp corner. Okay, so in that case, this is not going to be smooth. Okay, so whenever we talk about curvatures, we are going to talk about what is curvature of smooth curves. Okay, so now this curvature, in layman's language, what do you think curvature? Yes?
The tendency of bending the curve.
The tangential band. I want something more layman's language. I don't want any mathematics to be involved here.
The tendency of bending the curve.
Okay, that can be one answer. Okay, it is a measure of. Yes, it is a measure of how
the tangent.
No, again, I'm saying I don't want any mathematical concept here. Tangent, normal, all these things I don't want here. I want a layman answer. What a layman is going to think about. Suppose a non-mathematician is driving a car on a road, and all of a sudden he or she has to take a turn, right? Then he or she is going to say that, oh my God, there's a sharp curvature here. There's a curvature here. Okay, so basically it is the measure of how quickly a curve changes direction. A curve changes direction. Okay, changes direction. Fine. So now let me come back to this again. Okay. So here we were talking about tangent. Okay. And this condition allows you the existence of tangent at each point of this curve. Okay. And then you know that a unit tangent, it is simply defined by this. Unit tangent is defined by this. Okay. Then this measure, it is defined as the curvature, and it is denoted by the Greek letter, kappa, and it is defined as the magnitude of the rate of change of the unit tangent vector with respect to the arc length. Say, suppose at this particular point, my arc length is suppose this, okay? So this is S. Again, S is a function of t, right? So then this is defined as dt. This is defined as this curvature is defined as, okay? So now you know that your this one I can further decompose as dt by dt, right? ds by dt. Okay, is it okay to everybody? Right? So basically, this is derivative of the unit tangent vector with respect to t. So this means this is again t prime t, isn't it? Right?
Yes.
And if you recall, this s, it was defined as your something like a to t, then r prime u du, r prime u du, isn't it? Right? And from here we found out that ds dt, this is simply r prime t. Is it okay?
Yes, sir.
Fine. So that means here I can simply write it as r prime t. So we are going to make use of this expression in order to develop some theories for the formula of this curvature. Okay. So now before going to those, can we try to find out the radius of curvature of a circle of radius is in two-dimensional plane? Okay, suppose you are given find the not radius of curvature, sorry, only the curvature. I still haven't come to radius of curvature. I don't think I've come. Find the curvature of a circle of radius is radius t, right? And see here again, you know that t is given by again in terms of r. Okay, so then whenever I want to define this r for a circle lying on plane, if it is a circle of radius r, it is going to be a cos t, a sin t, isn't it? Right? So then your r prime t, so this is going to be equal to what? Your minus, sorry, a sin t, a cos t, fine. And then if you want to find out what is t, this unit tangent, so this is simply r prime t divided by its magnitude. Okay, and then so this is going to be its magnitude is what? It is simply going to be from here, it is simply going to be a, isn't it?
Yes.
Fine? So if you divide it by a, this is simply minus sin t cos t. Okay, so then if I want to find out again your t prime t. So this is simply minus cos t minus sin t.
Sir,
Yeah, did I make some mistake here?
yeah, you have written r prime t both the times
R prime t.
on the board.
T of t is equal to r prime t divided by mod of r prime t.
No, r
This
prime
one.
t. Oh,
Above,
above
above.
that.
In the first line, it will be
Oh,
r.
acha. This is RT. Yeah. This is RT. Thank you. This is RT. Sorry. This is RT. Okay. Thank you. This is RT. So I have got t prime t. I mean, this is equal to this. So obviously, mod of t prime t is going to be equal to 1, isn't it? So for a circular radius r, if I plug in this formula, this is mod of t prime t. From here, this is simply equal to 1. Okay, fine. And then mod of r prime t from here we have already found that is simply a. So it is 1 by a. It is 1 by a. Okay. See, does it give you some idea about I mean how much turn? I mean suppose you are on a circular road. You are on a circular road. Say what it tells you is that suppose fine. Okay. Say suppose I am drawing two road, which is circular. One has radius say a1, and the other one say suppose it has radius a2, where a2 is much bigger than a1. Okay. So then, if I consider the curvature at a point here, at a point here for this pink part and this blue part. Okay, what does it tell you? If you look at the blue part, you will see that it is almost like a straight line, isn't it? Right? It curvature is less because this curvature is given by 1 by a. Right? More the, greater the value of a, what is going to happen? Lesser is going to be the curvature. Right? So from here itself, it is obvious. Okay? Fine. So this is about. Yeah, so this is just an example. So now let us try to find out some more formulas for the radius of curvature. Okay, so over there, the radius of curvature it was for a circle. So now radius of curvature, is also expressed by this formula. This divided by r prime t whole cube. R prime t whole cube. Okay, fine. Okay, so how to go about it? You will see that this mathematical manipulation is very interesting here, and that is going to involve a lot of properties of whatever we have learned about vectors earlier. Okay. Okay. Say we know that your just a minute. What we have found out that your t, okay, t equal to r prime t mod of r prime t, right? And if s is the arc-length function, then you know that. So this is the vector. That is, then you know that this is simply ds dt, isn't it? Is it okay? This we already know. Okay. So this implies. Thank you. So this implies your r prime t. This is ds dt into t1. See, this is a scalar. This is a vector. Okay. So now, if I want your derivative of this, derivative of this. So then this is going to be the derivative of the scalar part. Just a minute. T plus ds dt t prime. Ds dt t prime. Okay, fine. Just a minute here. What I need. No. Sorry. This is R double prime. Yeah. Is it okay? Fine. If I again differentiate this with respect to t, then I'm going to get R double prime. Right? So then I'm going to get this. Okay. So now look here. So always remember. Always remember in the vector, cross product, Say, suppose I have something like say lambda 1a cross lambda 2b plus lambda 2c, where ABC are vectors and lambda 1, lambda 2, lambda 3 they are scalars. So what you should do? Always you should bring those scalar together, and then it is going to be A cross B plus lambda 1, lambda 3. This is going to be A cross C. Okay, so this is the way we have to follow it. There cannot be any exchange of those vectors. Its order has to remain intact. Okay, fine. So now, if we follow this, and then if I try to find out, R prime T cos R double prime T, so then from here, what is going to happen? So R prime T, so ds dt, and then this is d2s dt squared, then T cross T, right? And then plus ds dt whole square, your T cross T prime. Is it okay if I follow the same?
Yes.
That's
right. Okay. So now the interesting part here. So I have simply followed this one. The interesting part here is now, I'm not sure whether I discussed it earlier, is if you take your vector product of the same vectors, this is always zero. Because if you recall, the vector product of two vectors, cross product of two vectors, A and B, what is the formula? Mod A, mod B, sin theta, right? And the angle between, if the vectors are the same or they are in the same direction, they are in the same direction, angle between them is going to be 0. And sin 0 is 0. So that is why this is going to be 0. So from here, I am going to get 0 vector. Is it okay? Fine. And then today, not today, in my earlier class, we have found out that if you consider a vector having constant length, vector say V having constant length, then V and V prime are orthogonal, right? So now we have found out that this T is a unit tangent vector. So that means it is a vector of constant length 1. Is it okay? So from there, if I follow the same logic, from there we will find that T and T prime, they are orthogonal. Is it okay? Fine?
Yes.
So that is why now if I take from here the mod of this, so here I'm simply going to get ds dt whole square, and then mod of your t prime, okay, and then from here I am simply going to get here mod of t prime and then sine pi by 2, isn't it? Because they are orthogonal, and mod of t is 1, this is 1, so this is going to give me ds dt whole square t. Okay, fine. So that means your mod of t prime is equal to your mod of r prime t plus mod of r double prime t divided by, and again remember ds dt is simply mod of r prime t, isn't it? Fine.
Yes.
So that is why this is going to be mod of r prime t whole square, right? But I know that kappa is equal to mod of t prime divided by mod of r prime, isn't it? We derived this.
Yes.
Okay? So from here, if I make use of this, so this is going to be simply r prime t cross r double prime t, and with this extra r prime t, this is going to be r prime t. Okay, so there is another formula. I'm just simply going to give you how to prove that. This one. So this can also be, I mean, in Cartesian coordinate plan. Okay, so this is kappa x. If I consider a curve, say y of x, if I consider something like this, so this is y x. This is a function of. Okay, so if I want to find out the curvature of this, so then the formula for this is f double prime x and then 1 plus f prime x whole square to the power 3 by 2. That's fine. Okay, so now I'm just going to give you the how to do it because I don't have time to do all those stuff. Okay, so what you do now, see. I have told you that whenever you say, suppose I am parameterizing this vector in xy plane, so I am parameterizing which some function. I am parameterizing with some function of the single variable t, right? So now any point in R, any point in xy plane, say xy. So then R can be written as this, isn't it? Right? The components of R. I don't know what whether x is a function of t and y is a function of t. I don't know. That part I can take later on, right? But what I can do here, because y is a function of x, I can use my x as the parameter. Is it okay?
Yes.
Right? So now what you do, simply think x to be something like t. So that means from here what you are going to get, r prime, you are going to get 1
Y
y
prime
prime.
x.
Yeah. And then simply follow this. It is going to come out. Okay? So that is about your curvature. So now let us come to another important concept. normal and binomial vector. Normal and binomial. Okay, fine. Say, suppose I'm considering, say, a carving space. I'm considering a carving space like this. X, Y, Z. Okay. So then you know that if I consider any point, say, suppose this is the direction. Okay. So then you know that this is going to be my tangent. This is going to be a vector which is tangent to the point P. Sorry, tangent to the curve C at the point P. Is it okay? Fine. So now, see here we are talking about 3D curve. We are talking about 3D curve. It is something like this. Okay. Consider this to be the curve. Consider this to be the curve. Okay. So then, say suppose at this point I have this tangent. At this point I have this tangent. I have this tangent. Okay. Now there will be infinitely many directions I can find where I can find a vector. Like say in this way, I can find a vector like this, which is the normal to this, isn't it? I can find a vector like this, which is normal to this tangent. Is it okay with everybody what I'm trying to say? Yes, I can have like this. So there will be infinite, direction of vectors, which will be perpendicular to the tangent vector. Okay. But we have already found out that obviously the unit tangent vector, given by this, obviously it is in the direction of the tangent vector. It is in the direction of r. Okay, and we have already found out that this t and t prime, they are perpendicular to each other.
Yeah,
okay?
Because T has unit length.
Yes, right? This we have already found out. So that means for this tangent vector, I will always be able to find a unique direction for a vector perpendicular to this tangent vector, okay, which will be given by this. Okay, so I am going to choose the direction of this vector along the normal to this tangent. Okay, so then again from here what I am going to do, because I know that t prime is perpendicular to t, but that doesn't guarantee me that t prime is a unit vector. What I am going to do, I am going to choose a unit vector n bar given by t prime by mod of 3 pi. So definitely then this is going to be a unit vector. So then what is going to happen? So for this unit tangent vector, I will be able to find a unit direction. I'll be able to find out a unique direction in such a way that these two are perpendicular to each other. Okay. So this n bar, it is called the principal normal vector to the curve C at the point P. Okay, fine.
Yes.
And then what is happening? Now I know that T bar and n bar, they are perpendicular to each other. So obviously, if I take their cross product, if I take their cross product, so then, and of course, here one thing, your I'm going to assume that your r prime t is not equal to 0. That I have to assume. Otherwise, all these studies, it is invalid. Because if r prime t is 0, of course, if r prime t is 0, then the existence of tangent is also invalid, isn't it? Right? So obviously, if I take their cross product, so this is also going to be a vector which is perpendicular to both t and n. Okay, so it is going to be something like this. If I am considering this n and t on the plane of this blackboard, so then exactly I am going to have a direction like this. Okay, so this is along the direction of n cross t. Okay, and that is called the binomial vector. Binomial vector. Okay, so basically T, N, and B, it forms a triad. Okay, so they form some kind of that coordinate system. You can consider a local coordinate system by considering 3 axes along these 3 directions. Okay, so this is about what? Tangent, normal, and binomial. Okay, let us see whether we can do some exercise or not. Okay, fine. So, okay, let us start that. Say, let us consider our favorite example. Does it really a this vector represents which curve? Yes?
Circle? No.
No. Face.
Cylinder.
Helix.
Okay.
Helix. I did it some 3 classes ago. Okay, fine. So now if you have to find out the binomial, normal, and tangent. So obviously tangent is given by your unit tangent is given by this. So this is what? Minus sin t cos t1. So you know that this is square root 2, right? We did in our last class, right? It's square root 2. Okay, so just a minute. This is not t prime. This is simply t. This is the this is the unit tangent value. Okay, fine. So then, if you want to find out the normal vector, so unit normal vector. So then this is simply t prime by mod of t prime. Okay. So what is just a minute. Just one thing. In fact, one thing you don't need to worry about this because see, mod of t prime is always going to be 1, isn't it? Is it okay?
Yes.
Right? So that is why this n I can simply write as t prime. Okay. Is it okay? The mod of t prime, mod of t prime, I don't have to open in here. Or do I? No, mod of t prime no, sorry. T prime the mod of t prime is not sorry about that.
Yeah,
I
it is
I
not.
was wondering about this. Okay. See, let us try to find this out. Firstly, let us try to find out t prime. So t prime, so this is going to be equal to square root this minus cos t sin t 0, right? Sin t 0. So your mod of t prime is simply it is going to be 1 by square root 2, right? Yes. Okay.
Yes.
So that is why. So therefore, your that unit normal vector is simply t prime by mod of t prime. So this is simply minus this one cos t sin t, right? Yeah. Yes. That's right.
Yes.
Okay. So I think the binomial you find it yourself. Again, binomial is this. Right? Just one thing. Just give me a second. I just want one thing to be sure. Just yeah, this is fine. So this binomial, you remember, this one you should be careful about the order. It is always t cross n, because if it is n cross t, again it is going to be in the opposite direction. So that is why I had another look at it. You have to follow this. Okay. So then I mean you simply find it through this. Okay. And t prime was your this minus cos t sin t 0, and then this was minus cos t sin t 0, and from here you find it out. Okay, binomial. Okay, so this is about normal and binomial vector. I have already told you about principal unique normal vector. That is nothing but this one. Okay, and now another important concept. Motion in space. Basically, we are going to talk about velocity and acceleration. Velocity and acceleration. Okay. So here again, in terms of derivative, we will try to find out something. Okay. And as before, suppose I am considering a space curve. I am considering a space curve. So if I consider this space curve to be the trajectory of a particle moving in space, right? So then, if my parameter t denotes time, so then what is going to happen? What is going to happen? If I consider a point P here, and it is R, and if P is given by your xt, yt, jt, fine. And if after a while, after some time, delta t, the point P moves to the point Q, fine. So this is the vector R t plus delta t, okay, t plus delta t. So then, obviously, the derivative of the function, derivative of the vector value function, this is simply limit delta t tends to 0, your R t plus delta t minus r3 divided by delta t. Now remember, now t denotes time. Now t denotes time. So then you know that this is nothing but the velocity vector v. Velocity vector v. And from the formula that we devised earlier, so its component along x, y, and z direction is simply given by this. Simply given by this. Is it okay? Fine. And another interesting factor here is that if you recall, you may be thinking that how, I mean, here say if this vector, okay, whenever we consider it, and again, whenever we consider the derivative of the function with respect to time t here, then earlier what we found out that the derivative is along the direction of the tangent. Okay, so it is a vector. It is kind of it is. You may be thinking that okay, I am considering something like a rectilinear relation. If I look at this vector, okay. So now, when I consider the magnitude of velocity, it is simply the speed, isn't it? It is simply the speed, right, of the particle. Now, if I look at magnitude of velocity, so then you know that this is simply r prime mod of r prime t, right? And what did we find earlier? This is simply ds dt, right? So that means if you consider the arc length, if this is the actual distance covered by the particle, so then this ds dt is nothing but actual speed, isn't it? Earlier also, whatever you have done.
Yes.
Fine. And again, if we have to find out the acceleration, so acceleration is simply given by derivative of velocity. So it is going to be dv dt, and this is d2r dt2, and eventually it is going to be given by this. So I mean, in your tutorial sheets, you will have enough problems. So I don't want to spend much time on this. So this is just I mentioned the problem. So motion in space, velocity, and acceleration. So now I think we can move to function of several variables. Functions of several variables. Okay. So in fact, we are going to be moving to this actual multivariable calculus. Just let me shape up the. Okay, in fact, I'm trying to move towards partial derivative. Okay, so in MA 101, in single variable calculus, what you consider ordinary derivative. Okay, now I'm going to consider partial derivative. So you know that I mean the existence of single variable functions in real life. In fact, it is a rarity, because whenever we consider some function, I mean, if we want to express something mathematically, what is happening around us, you will see that it is always going to involve something like space and time. So in that case, at least you are going to have two variables. Okay. So whenever we consider, I mean, partial derivative, we have to consider function of more than one variable. variable. So that is why we are going to deal with function of several variables. Function of several variables. Okay. So to start with, what we will do, we will start with the simplest of them. That is nothing but function of two variables. Function of two variables. Okay. Fine. So now let us try to. So obviously, function of two variable, it is going to what? It is going to consist of more than one variable. And let me consider the variable to be x and y. So that is why we are going to use R2 such that we can consider an ordered pair. We can consider a point belonging to the xy plane in some domain. Okay, and that domain, let us consider that domain to be something like this. Okay, fine. So suppose I am considering a point xy in a domain D, belonging to R2. Okay, so then a function f from D to R, it is going to be what? It is going to be a rule in such a way that to each point x comma y belonging to D, I am going to have a unique point here lying in R. Okay, lying in R. Okay, and D is called the domain, and the set and the subset of R on which all the points like f of xy belongs, it is called the range of the function f. Is it okay? Fine. So your range of f is simply some write it as okay, something like z belonging to R, such that your j equal to f of xy, where your xy belongs to D, which is a subset of R2. So I can write it like this if you want to write it in detail. Okay, fine. So maybe let me do a quick revision of whatever I have done before. So let us start with the this is about curvature. And again, we have to remember that the curvature of C at a given point is a measure of how quickly the curve changes direction at that point. So this is what we found out. These are the two formulas that we were trying to figure out. And this formula 11, you please work out at home. And this is about normal and binomial vectors. So here you can see the triad. You can see that this T is the unit tangent to the blue curve at this point, and then we have found out its normal vector here. This is the principal unit normal vector here, and you can see that this vector V, which is called the binomial, it is perpendicular to both T and N. Okay, so this we have already done, and this is the illustration. And this is the motion in space, velocity, and acceleration. Okay, fine. So now what we are going to do, I am simply going to move to the functions of several variables. Okay, fine. So this I have already shown to you. A function f of two variables is a rule that assigns to each ordered pair of real numbers xy in a set D a unique real number denoted by f of xy. The set D is the domain of f, and its range is the set of values that f takes on. So that is this. So this I have already explained. And what I have already done is that we often write, j equal to f of xy to make explicit the value taken by f at the general point xy. Okay, and remember here x and y are independent variables and j is the dependent variable. And a pictorial description is like this, as I have told you. I was taking a variable point xy, so they have also taken a fixed point here. Okay, so it is going to be something like that. Okay, and what they have done, they are calling this real line as j-axis. Okay, and there's a reason behind that. I'll tell you what that is. Okay, so now what I would like you to have, you simply look at see the domain is what domain is nothing but the set of points that is being considered in R2, right, for this function of two variables. Okay, and range is, it is nothing but the set of real numbers like j, where j is given by f of x comma 1. Okay, fine. So let us try to work this out. You look at this. For each of the following functions, evaluate f of 3 comma 2 and find the sketch of the domain. Okay, so basically you are told to sketch the domain. I'm not even bothered about the value of the function of 3 2. This is pretty straightforward. But I'd like to ask you something else. Okay, fine. So just I will do that and then I'll finish. So okay, so the so exercise, first exercise. This is what x plus y plus this one. Okay, I'm trying to find out the domain of this function. See, if you want to find out the domain, you have to find out all those x and y in such a way that this function is well defined. This function you can define. Okay, the very first thing that you need to know is what? In order for the function to be well defined, your x plus y plus 1, that has to be greater than equal to 0. Is it okay? Fine?
Yes.
Yes. So, and then what from here, what you must have, x cannot be equal to 1. Okay, so then if you want to draw the domain of this function, so suppose I'm thinking about x plus y equal to minus 1. Okay, so when x equal to 0, y equal to minus 1. So this is a point, and when y equal to 0, x is minus 1. So minus 1. So basically, this line is x plus y plus 1 equal to 0, right? So since this is greater than equal to 0, I am going to take all points towards the right of this line, including this line, because greater than equal to 0. Okay, and then what I'll have to do, I have to exclude all the points in this line along the line x equal to 1. Is it okay with everybody? Fine?
Yes.
Okay? Right? So
Yes,
the
sir.
domain is going to be the set of all points lying toward the right of this straight line, including that straight line, and excluding the points on the line at line x equal to 1. Okay, And what was the second function given? Say g of x, or I think it was x y square minus x. Okay. So obviously, for the second function, in order to define the second function, what you must have, this must be what?
Non-negative.
Non-negative. So this must be, so y square minus x must be greater than equal to 0, greater than equal to 0. So that means x must be less than equal to y square, right? Y square is greater than equal to 5. Okay, so now if I want to draw this x equal to y square, if I want to draw x equal to y square, I'm going to have something like this. Okay, so if x has to be less than y square, so then what I must have? I must have everything towards its left. Okay, fine. So this shaded portion is going to be something like that. So I just one more exercise I want to do. I think they have another good example first. Yeah. 9 minus x squared minus x. Okay, so now what you have to do, you have to find the domain and range of the function. So earlier, you were told to draw only the domain. But now the question is finding the range as well. Okay. So can you tell me quickly what will be the domain? The such that
9 minus x square minus y square is non-negative.
That is greater.
Greater than equal to 0, right? So that I have to consider all the points lying inside this circle. X squared plus y squared equal to 9. Inside or on this circle, right? Okay.
Yes.
Domain you can found. So now the range of f. So range of f, it is going to be something like z belonging to R, right? Such that z is equal to f of x1. Right? So now.
Sir, H, not F.
Oh, h, yes.
There also.
Where? Yeah, here. Thank you. Because we are so much used to the function f. Okay, fine. Thank you. So now, if you look at this, what will be the values of j? So if I call j equal to h of x y, so j equal to your 9 minus x squared minus y squared. Now you can see that if your x squared plus y squared is less than equal to 9, then you know that 9 minus x squared minus y squared, that is always going to be less than equal to 9, isn't it? If xy belongs to D.
Sir, greater than equal to 0?
No. I'm not talking about greater than equal to 0. See, here, if you look at this expression, from here, what is the greatest value of x squared plus y squared? That is 9, right?
Yeah.
Right? And the minimum value is 0 there. Okay?
Yes.
Fine. So this expression is always going to be valued. So that means your j equal to positive square root of this. Positive square root of this is less than equal to 3. Okay. And again, what I know, just another thing. Yeah. J. Yeah. Since we are see here, let me tell you one thing. Whenever we are now going to, talk about functions like this. Okay. So here we are considering only the positive square root. If we consider the negative square root, then explicitly I am going to put a negative sign here. Okay. So from here also, if j equal to this, then j is obviously greater than 0. Okay, fine. So that means the range of j, or sorry, the range of this function is simply this, isn't it? So if this is so, then this is simply this interval. This is simply this interval. Okay, so your range of h is simply the interval -3 to 3. That's it. Is it okay? Fine.
Sir, 0 to 3.
0 to 3. Sorry. Yes. -3 cannot be, right? Because I want that to be positive. 0 to 3. 0 to 3. Sometimes I'm going to do, mistakes, intentionally, just in order to see whether you guys are attentive enough or not. Okay, fine. So that's it. So in my next class, I'm going to do limit and continuity of a function of two variables, and then that actual definition of your partial derivative. That is what I'm going to do. Okay. So I'm going to finish my class here itself.